Welcome. In today's video, we're going to focus on logarithms and in particular, learning to use logarithms, differentiating functions involving logarithms, and what I have here on the right-hand side is 20 rules that you must remember to succeed in calculus when it comes to exponentials and logarithms. And so I have a list of 20 rules, which I think are the most important rules that you absolutely must remember to have success in calculus. All right, so let's get started on the problem set here. So I'll begin with question 1, and along the way we'll refer to these rules. So in question 1, we're asked to solve for x. So let's see, question 1. Solve 2 to the power of x is 16. And now I've got a few different ways to do this. And you could do this in your head because you can notice that 16 is 4 to the power of 2. And then you could notice that 4 is 2 to the power of 2. And then here you see we can use an exponent rule. So which one is it? It's number 3. That a to the power of b all to the power of c is a to the power of the product of b and c. So we can see then that this is 2 to the power of 2 times 2, or 2 to the power of 4. Okay, so given that, we know now that 2 to the x is 2 to the 4, so clearly x is equal to 4. All right, but let's do this with logarithms as well while we're at it. So alternatively, and I'll just write alt for short, x is equal to log to base 2 of 16. And then with the same observation that 16 is 2 to the power of 4, we have log to base 2 of 2 to the power of 4. Now there's a log rule that says when we have an exponent inside the bracket of the log, so rule number 8, we can pull down that exponent and put it in front. Okay, so let's do that here. So 4 times log to base 2 of 2. Now what this means is, what number do we need to raise that base 2 to in order to get what's in the bracket? Well, it's 1 in this case, because 2 to the power of 1 is 2. So we have 4 times 1, which is 4. So again, we get 4. Okay, now what if you really, for whatever reason, in the stress or pressure of an exam, didn't know what to do and couldn't do either of these things? So what would you do in that case? Well, you would use a log rule that says you can change this to a log base of your choice. Now, on a typical scientific calculator, you have the natural log, or ln, and you have log to base 10. So you could take your choice here. So alternatively, again, we could say x is equal to log to base 2 of 16, which is the natural log, or log to base e, of 16 over log to base e, or ln, of 2, and then punch this in the calculator. You'll get a number for this, you'll get a number for this, and the quotient will give you 4.0. Okay, and so yes, you can solve it that way, but this, I would say, is the dumb way to do it, because you don't want to be a button presser, right? So if you go for this option, well, then in your mind you're resorting to just pressing buttons, which is not ideal, because the more of these things that you know, the more of these rules you know, and the more of these rules that you that are natural to you because you know them, through context, you'll just be better at calculus in general. All right, so I advise, don't be a button presser unless you have to. Okay, so let's move on to question 2. So in question 2, it says, solve for x. We have 3 to the power of x is 1 over 81. Okay, now let's begin with rule number 1. This is, we can swap 1 over 81 to 81 to the power of minus 1. Okay, and now you might notice that 81 is 9 times 9. So we have 9 squared to the power of minus 1. Okay, and then you might notice that 9 is 3 times 3. So we have 3 squared, squared, and then all to the power of minus 1. Okay, now we can use the log rules that says we can multiply those exponents. That's rule number 3 here. So we multiply the 2 and the 2 and we get 4. So we have 3 to the power of 4, all to the power of minus 1. And then let's do that again. So we now have 3 to the power of 4 times minus 1 is 3 to the power of minus 4 is 3 to the power of x. And now our task here was to solve for x, and so now we've got it because we can equate the exponents since we have the same base. So x is minus 4, and we're done. Except now let's do this with logarithms as well. So alternatively, 3 to the x is 1 over 81. Okay, now in logarithms, we want to solve for the exponent, and so here our base is 3, and this is the right-hand side, and so we can say alternatively, using rule number 4, that these two things are equivalent. That's what I mean by the arrow that goes both ways. These are equivalent, just different ways to express the same equation. So we have then x is equal to log to base 3 of 1 over 81. Okay, and now 81 is 81 to the power of minus 1. So log to base 3 of 81 to the minus 1. Now, which logarithm rule can we use to pull down that minus 1? Well, it's this rule number 8 again, very useful. So let's pull down the minus 1. So we have minus log to base 3 of 81, but 81 is 3 to the power of 4. So we can also pull down a minus 4, and then again we see that this is minus 4 times log to base 3 of 3, which is 1. So minus 4 times 1, which is minus 4. Okay, so we've done that in 2 ways. So let's move on now to question 3, where we're asked to solve for x in pi to the power of 2x is 20. Okay, and now let's see, if we solve for 2x using rule number 4, well then we can find x by dividing by 2. So let's do that. Using rule number 4, we have 2x is equal to log to base pi of 20. And this is the question here. What number do we need to raise pi to in order to get 20, remember? Right? And so that talks of this equivalent relationship between this log equation and the exponent equation. All right, so if we just divide throughout by 2, then we get our answer. So let's do that. X is equal to 1/2 log to base pi of 20. And this is our answer, but we could make this look in a more conventional way, right? Because remember, you don't have a log to base pi button on most scientific calculators. And so let's put this in a more conventional way using another log rule. So which one is it? Rule number 9. Now let's change this to a natural log. So we have 1/2 ln of 20, or log to base e of 20 over ln of pi. Okay, and you could get a decimal approximation for this, and if I remember right, this is something like 3 point something. Or am I thinking of something? I'm probably thinking of another problem that I've done. Okay, anyway, so you can calculate that. Now, can you put this in any other way? Well, we can take this 1/2 up into here and write that ln the square root of 20 over ln pi. Okay, that's using a log rule and an exponent rule. All right, let's move on to question 4. So in question 4, it says solve for x, where we have e to the power of minus 3x is 100. Okay, so we have minus 3x is the natural log of 100. So if we divide throughout by minus 3, we have our x, but we can tidy this right-hand side up a little bit because 100 is 10 squared, so we have natural log of 10 to the power of 2. And then we can bring that 2 down and say that minus 3x is 2 times ln of 10. And then divide throughout by minus 3, so x is equal to minus 2/3 ln of 10. And that I see as a reasonably simple answer. All right, so one of the nice things about logarithms is that if you have a huge number inside here that's a power of something, you can take that exponent out in front using rule number 8. Okay, so let's have a look at another example here, e.g. if I have natural log of, say, 10 million. Is that 10 million? Okay, I'll put the commas in so it's clear. 10 million. Natural log of 10 million. Well, this would be a bit of a pain to say and a bit of a pain to enter into a machine. Okay, so you can count how many zeros. We've got 7 zeros. So that makes this 10 to the power of 7 inside the brackets. ln 10 to the power of 7. And then you can bring down that 7 and call this 7 times ln of 10. All right, so that's one of the nice things about logarithms. So let's move on now to question 5. Where it says, solve for x, the equation 6 log to base 30 of x is minus 3. Okay, so the first thing you would want to do is divide throughout by 6 and then swap forms from the log form to the exponent form because x is inside the bracket of the log function. So dividing throughout by 6, we have log to base 30 of x is minus 3 over 6, which is minus a half. Okay, and so now let's change form, putting x as the right hand side, but I'll swap sides and say x is equal to 30 to the power of minus 1/2. Now I can put this in perhaps a more familiar way by saying that this is, and then I'm using this rule number 1, so we have 1 over 30 to the power of 1/2. And then 30 to the power of 1/2 is the square root of 30. So we have 1 on 30 is our x. Okay, so let's move on now to question 6. Now for question 6, I'm going to need a few log rules and I'm going to need a fair amount of paper because number 6 is quite tricky. So I'll just grab some new paper here. First, okay, question 6, we are asked here to solve for x to the power of log to base 10 of x equals 1000 x squared. So the first thing I want to do, now I notice you've got x in 3 different places, right? And so it's in the base, it's here. All right, so what I want to do here first is change from the exponent form to the log form. All right, now have a look. In the exponent, that's our b. In the base x, we've got our a. And on the right-hand side, we've got our c. All right, so let's label these according to the rule. This is our a. This is our b. And then the right-hand side is our c. Okay, and so let's swap forms here. So this would say log to base 10 of x equals log to the base x, log base x, 1000 x squared. All right, so now we've changed to the log form of this equation, but it looks just as complicated, right? And so now what we want to do first is use the rule that says that the log of the product is the sum of the logs. And so which one is this? That's rule number 6. Okay, I'll put this in view. This says log to base a of b times c is log to base a of b plus log to base a of c. So let's break up the right-hand side in that way. So we have log to base x of 1000 plus log to base x of x squared. Okay, and so the reason I wanted to do this is because now I can see that I can use the rule that says I can bring down that exponent of 2 and say that this is 2 times 1 in this second term here. So let's do that. We have log to base x of 1000, but 1000 is 10 to the power of 3. And then here we have 2 times log to base x of x, which is 1. So I'll just leave this as 2, but it's 2 times 1. Okay, now let's write our left-hand side again so it's close. Now what do we have? Is this any easier? I can bring the 3 down, right? But then I need to do something to make these bases the same. Okay, so now let's try to do that. And so how do I change the base here? Which rule do I use? I use rule number 9. So we'll bring the exponent 3 down using rule number 8, and then we'll use rule number 9. So we have 3 log to base x of 10 and then plus 2. And now I really want these bases to match, so I'm going to change base to base 10. So we have 3 times log to base 10 of 10 over log to base 10 of x. And then we had this plus 2. Okay, and so now log to base 10 of 10 is 1. So we can write this as 3 over log to base 10 of x. And then we have plus 2. Well, let's rewrite our left-hand side. Okay, and so now if we can only find what log to base 10 of x is, then we can find what x is, right? So now what we need to do is set out letting y be equal to log to base 10 of x, and then solve for y and hence get x. So that's the strategy here. Okay, so we'll let y be equal to log to base 10 of x. And so what does this equation become? Well, then we get y equals 3 over y plus 2. And if we take this equation, multiply both sides by y, we'll get a quadratic. Okay, so let's do that. Multiplying by y, we have y squared equals 3 plus 2y. Now you want to take these two terms over to the left-hand side so you get a quadratic equation. And if you solve the quadratic equation, you find y, and hence you can get x. And that's the strategy here. So let's continue. So y squared minus 2y minus 3 is 0. Let's factorize this now because it's easy. 3 is 1 times 3 and the difference is 2. So we factorize this as y with a 1 and y with a 3. Let's work out the signs. This is negative, so 1 takes a positive and 1 takes a negative, but the coefficient of y is negative, so we want our larger number to carry the minus sign. So that when we expand this out, we get minus 2y in the middle. Okay, so this tells us then that we have y equals minus 1 or y is equal to 3. Okay, so given that, let's then take these two back up here and see what this says from this point of view. So we have log to base 10 of x is minus 1, or log to base 10 of x is 3. Okay, so with these, we can change form using rule number 4. All right, we want to change from the log form to the exponent form. So here we have 10 to the power of minus 1 is x. So x is 10 to the minus 1, which is 1 over 10, 1/10. Or x is equal to 10 to the power of 3, which is 1,000. Okay, so we've got 1,000 or 1/10. And you can take these two answers and sub them back into the original equation and check that it works. It will work. Okay, well that was a tricky one. Let's move on to an easier one in question 7. So question 7 asks us to solve for x in log to base 2 of x plus log to base 2 of 7 equals log to base 2 of 21. Now, first thing to notice is that everything is in the same base 2. Okay, so we can take the left-hand side and marry it up using log rule number 6. That the log of the product, it's the sum of the logs, except we want to go from the sum to marrying that up in terms of log to base 2 of x times 7. Okay, so let's do that with our left-hand side. We have log to base 2 of 7x is log to base 2 of 21. Okay, and now the insides must match because the base matches. So what we have then is 7x is 21, and now it's easy, right? We just divide throughout by 7, and we get x is equal to 21 over 7, which is 3. And we're done with question 7. Okay, let's move on to question 8. And we're almost up to the calculus questions. So in question 8, we're solving for x, 3 log to base 10 of 2x minus 1 is equal to 1. Okay, let's divide throughout by 3 first. So we have log to base 10 of 2x minus 1 is equal to 1/3. Now let's change to an exponent form of this using rule number 4. So then we have 2x minus 1 is equal to 10 to the power of 1/3, and this is the cube root of 10. So you can put what looks like a square root, and then you just poke a 10 in that little crack. Or sorry, poke a 3 in the little crack. And so this refers to the cube root of 10. Now this, because 2 times 2 times 2 is 8, which is, I guess, near 10, this is 2 point something as a decimal number. Okay, and so now let's finish this off by adding 1 to both sides and then dividing throughout by 2. So we get x is equal to 1 plus the cube root of 10 all over 2. All right, let's move on to question number 9. And we're asked to solve for x again. Log to base 10 of 12x squared minus log to base 10 of 3x is equal to 3. Okay, we want to use a log rule that says that the difference of the logs is the log of the quotient. So which one is this? It's number 7. Log to base a of b over c is log to base a of b minus log to base a of c. So we can pack these two together in a quotient. So we get log to base 10 of 12x squared over 3x is equal to 3. Okay, so let's simplify this. So x is non-zero here. So log to base 10. Now that quotient 12x squared over 3x, we can simplify this because x is non-zero as 4x. Okay, now let's take this and use the exponent form of this log equation. So we have 4x equals 10 to the power of 3, which is 1,000. So dividing 1,000 by 4, we've got x is 1,000 over 4, which is 250. Okay, let's move on to question 10. Solve for x. Now, you see here in question 10, it says log to base e. Another word for that is the natural log. So here let's write ln 4x minus 1, because a lot of you will prefer ln because you have it on the calculator, or maybe you have a teacher that's used ln. Okay, minus 3 ln 9 is equal to 2 ln of 3. All right, so that's another way to say that. Now, we probably want to take this minus 3 ln of 9 over to the right-hand side. So let's do that. So we've got ln 4x minus 1 is equal to 3 ln of 9 plus 2 ln of 3. Okay, now 9 is equal to 3 times 3, or 3 squared, right? And so I want to do that because I have a 3 inside my bracket here. So I think it'll be easy if we just add like terms. So that's the plan here. Okay, so let's see this as 3 times ln of 3 squared plus 2 ln of 3. Okay, and so again, according to the plan, I wanted to pull the 2 down and call this 3 times 2 ln of 3 plus 2 ln of 3. So let's do that. So 3 times 2 is 6. 6 ln of 3 plus 2 ln of 3. Okay, how many ln of 3's do I have? I have 6 plus 2 of them, which is 8 of them. So we have 8 ln of 3. Now I can go the other way and I can put that 8 up into the exponent. And so we are using rule number 8 in the other direction. So we have then ln of 3 to the power of 8. Okay, and so now same base. So what we see then is that 4x minus 1 is 3 to the power of 8. Now let's solve this for x. Add 1 to both sides, divide by 4. And so we have x is equal to 1 plus 3 to the 8th all over 4. Okay, so if I do a little bit of mathematics in my head here, now 3 to the 8th is 9 to the 4th, or 81 squared. And so let's just multiply this out. 81 times 81, 8, and then 8 times 8, 64. So we have 6561 for 81 squared. So 6561 plus 4 is 6562 over 4. Now 6562 divided by 2 is, let's see, so we'd have 32 plus 25, right? Oh, I better just do this on the machine. Okay. 6562 divided by 4. And I'll put in a 0.0 there so I get a decimal number. So this is equal to 1640.5. All right, let's move on to the next question. I'm going to turn the paper over here. Next one says differentiate, and this is question 11 on my list. So we've got y equals 4 to the power of 6x, and we're asked to differentiate that. Okay, so I want to use an exponent rule that says that I can change this 4 into my own, well, favorite base if I had a different base here, but I can change it to base e. So let's do that using rule number 5. We have e to the power of the natural log of 4, and that's all to the power of 6x. Using rule number 5. Okay, next we can use the rule number 3 to multiply the exponents. And then, so if we do that, we've got y is equal to e to the power of 6 ln of 4 times x. All right, so now we want to differentiate this. So let's apply d on dx to both sides. But before we do that, because we're going to need the chain rule, which is down here in rule number 11, so I want to express this as e to the power of u, where u is equal to 6 natural log of 4 times x. Okay, now using the chain rule, rule number 11, dy on dx is dy on du times du on dx. Now y is e to the u, so I'll express the left multiplicand as d e to the u on du, or d on du of e to the u. Now I'm thinking of this as a differential operator operating on this. Okay, and then we multiply that result by du on dx, but u is this, and so I'll put this as a function of x here and say that I'm differentiating with respect to x 6 ln 4 times x. All right, now the derivative of e to the u with respect to u is e to the u. And the derivative of 6 ln 4 times x, which we can think of as a constant times x, it's just that constant 6 ln 4. So 6 ln 4. All right, now what was e to the u? Well, e to the u is this, but remember how we got that? It's this. It's 4 to the power of 6x, and that would look better on paper than e to the power of 6 ln 4 times x, right? And so let's go back to 4 to the power of 6x for this e to the u. And so I'll put the constant number on the left-hand side of that so it doesn't get confusing. And then let's swap now to Newton's notation. Y dash of x is equal to 6 ln of 4 times 4 to the power of 6x. Now, I like to use Leibniz's symbols for the action of differentiation because there are a lot of nice aids to memory in using Leibniz's symbols. But then at the end, once I'm done with differentiating, to display it, I'll go back to Newton's symbols because I find those more convenient in case I might need to sub in a value of x, right? Because these are less awkward in that setting. So I'll point this out to you, which shows you why I do this. And by the way, I mean, I find these much easier to use in integration, because integration is arguably more difficult than differentiation, or finding the antiderivative of a function, going the other way. And these nice aids to memory in thinking of these as if they were fractions, but they're not, of course. They just, in many ways, follow the rules that fractions would follow, which makes it nice to be able to use those because you can easily remember the rules of differentiation and integration using Leibniz's symbols. But then, when you display it, Newton's notation is often more convenient. And so I'll show you why this is awkward if you then want to sub in a value of a. So y dash of a means take the value x equals a and sub it in for x in the derivative, but in Leibniz's symbols, this is corresponding to dy on dx with a vertical line here, and at the bottom we would say x equals a, or just an a, right? So this is a lot more to write than this is, right? And so I use these symbols for the action of differentiation and the action of integration because they're very useful in helping you remember the rules and to get things accurate and to be fast about it. But then Newton's notation is, in my opinion, more convenient for using when you're subbing in a value. Okay, so let's move on now to the next question. I need to grab some more paper. So I'll take some of those pages and turn them over. All right, so now we are up to question 12, and this one is a lot like the previous one, so you might want to pause the video and work on this yourself and then resume and see what I did, because it's almost identical in the process to question 11. So y equals 10 to the power of x to the power of 6. All right, so this exponent is getting powered to the power of 6. And we're asked here to differentiate this. Okay, so first we will want to use rule 5 to change to base e and call this e to the natural log of 10 and then times x to the power of 6, because after I do this, I'm using rule number 3 to multiply the exponents. All right, and so this, we will want to call this e to the power of u, where we're letting u be equal to that exponent ln of 10 times x to the power of 6. All right, and so now we want to differentiate y with respect to x, but we can see that it's a function of u, and u is a function of x, so we need to use the chain rule, rule number 11. So dy on dx equals dy on du times du on dx. Now y is a function of u, so next we want to differentiate, so let's think of these as differential operators operating on that y, which is e to the u, and then multiply the result by the derivative with respect to x of u, but we want to express u now in this one as a function of x. So ln 10 times x to the power of 6. Okay, let's continue. The derivative of e to the u with respect to u is e to the u. And the derivative of ln 10 x to the 6 with respect to x is, so we have a constant times x to the 6. This is polynomial. This ln 10 is a number. So we bring the 6 down. So we have 6 ln 10, and then we subtract 1 from that exponent. Okay, and now we're pretty much done. We do need to change the u back into a function of x. And so we could just sub in ln 10 x to the 6, but e to the u is this, which is this, and this, in my opinion, looks better. So let's go for that form of it. Now we want to keep this number, and in fact the whole polynomial part on the left-hand side, so it doesn't look like it's part of the exponent. So now let's change for Newton's notation. Y dash of x is 6 ln 10 times x to the 5th times, and I'll put a dot for the times, 10 to the power of x to the 6th. And we're done. Okay, so let's now move on to question 13. Gonna move this up now, and I've got a total of 25 problems here. All right, let's turn the page over. And incidentally, you might be wondering what my other rules are. So after the 3 rules, chain rule, product rule, and quotient rule, I have an identity that relates E, or exponents and logs, to periodic functions, cos and sine, right? It's not my identity, of course, but it's an identity that I thought important enough to include on this list of things you must remember. E to the power of I times x, where I is the square root of -1, is equal to cos x plus I sine of x. Okay, and since we see that logs and exponents are related to trig functions, the rest of my rules here are rules for differentiating sine and cos. So the derivative of sine is cos, the derivative of cos is minus sine. Remembering that tan of x is sine of x over cos of x. Remembering that cos squared plus sine squared is 1, or that the point cos x comma sine x parameterizes the unit circle. And then these are 2 double angle formulas, and these are mostly useful in tidying things up or in integration. When you're asked to find, say, the integral of sine x times cos x, well, then you would want to swap this for 1/2 sine 2x before you integrate, because that'll make it much easier. Okay, so these are the 20 rules that I think you must remember to be very successful in calculus. And now, of course, there are a few others, things like the definition of sec, which is 1 over cos. The definition of CSC, or cosec, is 1 over sine. The definition of cot, which is the multiplicative inverse of tan, or cos x over sine x. And then, there are a few others. But these are the 20 rules that I think you must remember to succeed in calculus, or the 20 most important rules that I would memorize. Okay, so put these on some flashcards and just learn them. All right, so let's continue here. What have we just done? We've just done 12, so let's move on to 13. So question 13. We've got y equals 0.6, but let's write 0.6 as 6 over 10, which is 3 over 5. Okay, and then let's write the log to base e as ln. So, and then I like to put the number in front so it doesn't get confused with the exponent. So I'm just rephrasing this expression before we begin. Okay, so here's our function. Now we're asked to differentiate this. So look at its form before you even write anything down. What form have we got? We've got a constant times a natural logarithm of a function of x. Okay, so in other words, it's a function of a function. And so we need to use the chain rule and set out a u. So let's say that this is 3/5 ln of u, where u is equal to 3 plus e to the power of 5x. All right, now dy on du, using rule number 11 down here, the chain rule, sorry, dy on dx is dy on du times du on dx. Okay, now dy on du is d on du of 3/5 natural log of u. So I'll view this as operating on that function of u. Okay, and then we multiply the result by the derivative with respect to x of 3 plus e to the 5x. Okay, great. So now rule number 10 says that the derivative of a natural log is 1 over that variable, right? See these two letters match? We have 1 over x here. So in this case, the 3/5 goes through the differential operator. So 3/5 derivative of, so d on du of natural log of u, and then here that differential operator distributes over that sum and applies to the 3 and to the e to the 5x. So 0 for the 3, and then plus the derivative with respect to x of e to the 5x. Okay, now let's use this rule, rule number 10. This derivative is 1 over u, so we have 3/5 1 over u, and then over here we need to swap this using, let's set out v equals 5x, and so we would use the chain rule here. So let's set this out. This is d e to the v with respect to v times dv on dx, but remember I said v is 5x. So it's over here, v equals 5x. All right, so this derivative here is just e to the v, which is e to the 5x. So 3 on 5u, then we have e to the 5x, and then the derivative of 5x with respect to x is just 5. Okay, and so now what remains is to just tidy this up. So this is y dash of x. So we can see 5 divided by 5 is 1, so we can cancel the 5's. And so this is 3 e to the power of 5x over u, but u is equal to 3 plus e to the 5x. Okay, so this is y dash of x, and we're done with that problem. All right, let's move on to question 14, where we have a product to differentiate. So y equals 5x squared e to the 2x. All right, now I'm going to apply d on dx, the differential operator, to both sides. So we have dy on dx. And now remember the 5 comes right through that. So 5 d on dx of the product x squared e to the 2x. All right, now let's identify, let's call this one u, and this one, this exponential, let's call that v, so that we're now looking at rule number 12, the product rule of differentiation. Okay, and now I see this rule as the following. Pull one of these out the front, differentiate the other one, and then swap that around and add the result together. Okay, so I'll leave a little bit of space here. I'll show you what I'm doing, and then I'll fill in the rule here. So we've got 5 outside of this sum, v e to the 2x times the derivative with respect to x of x squared, and then we swap this around. So put the x squared out the front and differentiate the other one, e to the 2x. Okay, but what rule have I used here? This is u, this is v, so I've got 5 v du on dx plus u dv on dx. And I typically won't write this because you can see clearly what to do if you know the product rule. All right, so let's continue and differentiate these two items and simplify. The derivative of x squared with respect to x is 2x. And the derivative of e to the 2x with respect to x is 2e to the 2x. And you can use the chain rule to do this and set out more details if you like, but once you're really good at it, you can be a little bit faster about it. Just know your abilities. So if you're very new to this, then fully set it out. If you're feeling more confident, then you can take a little bit of a shortcut here and just write down this derivative because clearly you can do it in your head. So we have x squared, and then we have 2 e to the 2x. All right, so now what we should do is simplify this. All right, let's expand our 5 and put it in, but then let's pull it back out. So I guess I should say let's pull the 2 out and combine that with the 5 and call this 10. Now, what's common here? An e to the 2x. There's also a common x. So 10x is common and e to the 2x is common. So what remains then when I factorize out 10x e to the 2x? Well, what would remain is a 1 here and a single x here. So 1 plus x. Okay, and so this is y dash of x. Let's put this in a nice order. So we'll say y dash of x equals 10x, x plus 1, e to the 2x. And that x here looks a little bit like a bracket, but I mean it to be an x here. So 10x, x plus 1, e to the 2x. All right, let's move on now to question 15. Differentiate p equals 3e to the 2n plus e squared all to the power of 8. Okay, so what's the structure of this? We have a function of n all to the power of 8. So let's call this u to the power of 8. And you want to be careful because if you write fast, u's and n's can look a little bit similar. Okay, where u is equal to e squared plus 3e to the 2n. All right, now we want to differentiate p with respect to n. So dp on dn is equal to dp on du times du on dn. Now p is u to the power of 8. So we're differentiating with respect to u to the power of 8. And then multiplying the result by, and here's an example of how those two are looking similar. Okay, by d on dn of e squared plus 3e to the 2n. Okay, so we apply this differential operator to both of these terms. So because e squared is just a number, the derivative with respect to n gives 0 there. Now the 3 will come through the operator. So let's write our next line. Pull the 8 down, so we've got 8 u to the power of 7. And then times 0 plus 3 d on dn of e to the 2n. All right, now you know how this e to the 2n differentiates with respect to n because by now you've probably done this enough. So using the chain rule, you would generate an extra 2 because you would differentiate e to the 2n with respect to n also and multiply. Okay, and so we have 8 u to the 7. 3 times 2 is 6. And then times e to the 2n. All right, so now what remains is to simplify this. So we have 6 times 8 is 48. So 48. Now u is e squared plus 3e to the 2n, and that gets powered to the power of 7. And then we have times e to the power of 2n. Okay, and this is p dash of n. All right, so we've done that question 15, so now we need to move on to question 16. So in 16, we've got y equals log to base 10 of x to the power of 4. All right, and so it seems natural to use a log rule to pull the 4 down. So y equals 4 log to base 10 of x. And now we want to change to base e so that we can differentiate and use our rule number 10. So we change base using rule number 9 first. So this is 4 ln of x over ln of 10. And now let's write this so that it appears like a constant times ln of x. So y equals 4 over the natural log of 10 times ln of x. Okay, so it's a constant times ln of x. So now when we apply our differential operator d on dx, this constant can go through it, and we apply to ln of x, and now we can use rule number 10 to get 1 on x for this. So we've got y dash of x is equal to 4 over ln 10 times 1 over x, which we can write as 4 over ln 10 multiplied by x. Okay, well that one was easy in my opinion. Let's move on to question 17. Y equals log to base 2 of 9x. All right, so let's break this up using rule number 6. The log of the product is the sum of the logs. So we have then log to base 2 of 9 plus log to base 2 of x. But now we can also at the same time use rule number 9 and say that this is the natural log of x over the natural log of 2. Okay, and so now let's apply our differential operator d on dx, noting that this is just a number right here. So dy on dx is equal to 0 plus 1 on ln 2 d on dx of ln of x. All right, and so now we use the log rule number 10. The derivative of the natural log of x with respect to x is 1 on x. So we have 1 on ln 2 multiplied by x. Okay, question 18. Says differentiate y equals log to base 7 of x squared plus 1. So we want to change base here and put this in base e. So ln x squared plus 1 over ln 7. Now, let's say u equals x squared plus 1. So we have ln of u over ln of 7. Okay, now we use the chain rule. So dy on dx is dy on du, du on dx. So that is d on du of ln u over ln 7, and then we multiply this by du on dx, but u was x squared plus 1. All right, so du on dx is 2x. Okay, now the derivative of ln u with respect to u using rule number 10 is 1 on u, and the 1 on ln 7 can go through that operator. So we have 2x over ln 7 times d on du of ln u, which is 1 on u. So 2x on ln 7 ln u. Or sorry, just u, right? So we have 1 on u. And so u was x squared plus 1. So we have 2x over ln 7 and then times x squared plus 1. Okay, let's move on to another question. Which would be question 19. Y is 2 times the natural logarithm of 3x squared minus 1. And let's say u equals 3x squared minus 1, so this is 2 ln of u, where u is 3x squared minus 1. Okay, using the chain rule here, dy on dx is dy on du times du on dx, and so that is d on du of 2 ln x, but the 2 can come through, sorry, ln u, and then this gets multiplied by du on dx, but that's the derivative with respect to x of 3x squared minus 1. Okay, so using rule number 10, this is 1 over u, so 2 over u, and the derivative of 3x squared minus 1 with respect to x is just 6x. And so we have 12x over u. But u is 3x squared minus 1. And so here's our y dash of u. Okay, question number 20. And let's scroll up a bit. All right, differentiate s equals ln of sine squared of t with respect to t. Okay, so look at the structure of this. We have a function of a function of a function. So let's let u be equal to sine squared of t, or sine t all squared. So we have ln of u, where u is equal to sine squared of t. And let's say that this is the square of sine of t, and so that's v squared, where v is sine of t. Okay, so we have a function of a function of a function. Now, using the chain rule, ds on dt, that is ds on du, because s is a function of u, du on dv, dv on dt. All right, so this is our chain rule here. Now, s is a function of u, it's ln of u. So we have the derivative with respect to u of ln of u, and then we multiply this by du on dv, so u is v squared, so we have d on dv of v squared, and then dv on dt. V is sine of t, so the derivative with respect to t of sine of t. Okay, now using rule number 10, this is 1 on u. The derivative of v squared with respect to v is 2v. And the derivative of sine, using rule number 15, is cos. So cos of t. Okay, now v was sine squared. No, sorry, v was sine. And u was sine squared. So we have 2 sine t over sine squared t, and then times cos of t. Okay, and so we can cancel one of the sine t's, and we have 2 cos t over sine t. Now, I spoke earlier that cos over sine is called cot, so the answer to this question is this is 2 cot of t, or 2 cos of t over sine of t. Okay, so let's move on now to question 21. So differentiate y equals the natural log of 4x minus 3 to the power of 3. So here I'm going to view this in a particular way. I'm going to, because it looks, in my opinion, it looks a little bit ambiguous in the way it's written, because you could think of this as if it were saying log of 4x minus 3 and then all of that to the power of 3. So in other words, where is the bracket? So it could be out here, or it could be this to the power of this. I'm going to assume that it's 4x minus 3 to the power of 3. And I'll insert another bracket in here. So now it's pretty clear what is meant, right? All right, so we can say then that y is equal to 3 using rule number 8, 3 ln of 4x minus 3, which is 3 ln of u, where u is 4x minus 3. Okay, now using the chain rule, dy on dx is dy on du times du on dx. So here y is 3 ln u, so let's let the 3 come through the operator. So we have 3 d on du of ln of u, and then multiply the result by du on dx, or d on dx of 4x minus 3. Okay, now using rule number 10, this is 1 on u, so 3 on u, and then the derivative of 4x minus 3 with respect to x is 4. And so we have y dash of x is 12 over u, or 12 over 4x minus 3. All right, question 22. And you know what, I think I just need to get up and grab some more paper soon. Maybe even now. So give me a sec. All right, back in business. Where were we? 22. Okay, question 22 says, differentiate y equals 6x squared ln of 5x. So we need to use the product rule here and the chain rule, but you see the structure is we have a product of two things, and then later we'll use the chain rule on this one. Or you know what, we could even break it up, right? And so we'll probably break it up because that looks easier. So applying d on dx to both sides, dy on dx is equal to 6 d on dx of x squared ln 5x. Okay, so here is a u and here is a v. So we need to use our product rule, rule number 12. Let's keep the 6 on the outside. So 6 bracket ln 5x times the derivative with respect to x of x squared. And then we swap these around. X squared d on dx of ln 5x. Okay, the derivative of x squared with respect to x is 2x. Let's put that in front. So we have 6 outside of 2x ln 5x. And then for this one, now let's break that up. So we are differentiating the sum ln 5 plus ln x. Okay, it's hard to read there, but I've got the derivative of ln 5 plus the derivative of ln x. All right, now the derivative of ln x with respect to x is 1 on x using rule number 10. The derivative of ln 5 with respect to x is 0 because this is just a constant. And so we have 6, 2x ln 5x plus x squared on x. Okay, and now we simplify this, and this will get x for that. And so then we'll call this 6x outside of 2 ln 5x plus 1 because I've factored out the x out of this as well. Okay, question number 23. Y is equal to 8 ln x over x. All right, so here we have a quotient. That's the structure of this. It's a u over v. So let's write this as 8u over v. All right, and so now applying d on dx to both sides, dy on dx is 8 d on dx of that quotient of u over v. And so now we want to use the quotient rule, which is rule number 13 down here. So we have 8 over v squared, v du on dx, minus u dv on dx. Okay, where v is x and u is ln x. So let's write that here. U is ln x and v is just x. Okay, fantastic. du on dx is 1 on x. So let's write 8 over v squared. Now v is x, du on dx. So we're differentiating ln x. And then we swap those around and subtract. So minus ln x d on dx of v. But I'm running out of space here, and I'll just put, so dx on dx is 1. Okay, so I'll just leave that out. All right, great. So the derivative of natural log of x with respect to x is 1 on x. So x over x is 1. So we have 8, 1 minus ln x, and then that's all over v squared, but v was x, so this is all over x squared. And that's y dash of x. Okay, great. Let's move on to question 24. So in 24, we have y equals the natural log of a quotient of two things. Now, you could set out the chain rule and then the quotient rule, but I think that's a bit messy. So I would rather use a log rule here and break this up using rule number 7, saying that this is a difference of two natural logs. So y equals ln of 2x minus ln of x plus 1. Okay, now this one here I can break up again using rule number 6. Y is equal to natural log of 2 plus natural log of x minus natural log of x plus 1. Okay, and now let's apply d on dx to both sides. So dy on dx is, now the derivative of this number is 0. D on dx of natural log of x, and then minus d on dx of the natural log of x plus 1. And so for this you do need the chain rule, but so if you would set out u equals x plus 1, then you'd have d ln u on du times dx plus 1 with respect to x. And so for that second derivative there, that would give you 1, because the derivative of x plus 1 with respect to x is 1. And so you just get 1 on x plus 1 for this derivative here. And for this you get 1 on x. Okay, so here we get 1 on x minus 1 on x plus 1. And we can combine these two, placing these over the same fraction bar or vinculum. Say y dash of x is equal to x plus 1 minus x all over x times x plus 1. Okay, now the numerator of that fraction simplifies to be just 1. So we have 1 over x times x plus 1. And this is what you would get if you use the chain rule and then the quotient rule on this, which is arguably a bit more work than this. All right, last problem in the list is question 25. But as we write this, let's rephrase this as a power of a half. Okay, so 25, y equals x plus the natural log of 3x all to the power of a half. Okay, so it's clear that we need to use the chain rule for this one. So let's call this y equals u to the power of a half, where u is x plus ln of 3x. So dy on dx is dy on du times du on dx, which is d on du of u to the 1/2, and then multiplied by d on dx of u, or x plus ln 3 plus ln x, if we break that up using rule number 6. Okay, now differentiating these, we've got y dash of x equals 1/2 u to the power of a half minus 1 is minus a half, and then the derivative of x is 1. Keep the bracket in place. The derivative of log 3 is 0. The derivative of log x, natural log of x with respect to x, is 1 on x. All right, so now what remains is to simplify this. So this is u. And so we can now write y dash of x is equal to 1 plus 1 on x. Here's our numerator. Our denominator is 2 times the square root of u. Okay, can we simplify this anymore? I believe we can by multiplying top and bottom, or numerator and denominator, by x. And so that tidies up the look of this, and so we get x plus 1 all over 2x square root x plus ln of 3x. And we're done. Thank you very much.